Hello dear students, welcome you all. So in this lecture I am going to discuss about the delta modulation. Right? So delta modulation is another type of pulse code modulation. We have earlier discussed about the pulse code modulation, then differential pulse code modulation, and now we are arrived at a delta modulation. So these all are the same thing, but they are differ in terms of their working. Right. We have seen when we discussed the case of differential pulse code modulation, that differential pulse code modulation is suffering from some drawbacks. Right. The main drawback of differential pulse code modulation was the high bit rate and a large channel bandwidth required for the transmission, right, of these DPCM signals. Right. You can see here in PCM signaling rate and the transmission channel bandwidth are quite large. The same problem with PCM and DPCM. Although in DPCM we have slightly a lesser bit rate and the required channel bandwidth is small as compared to PCM, but still it is very high. It is creating problem for the transmission of DPCM signals. So to remove this problem, to address this problem, a new type of pulse code modulation was invented, and that was known as a delta modulation. Now, what is the working principle of delta modulation? The working principle of delta modulation is very simple. It is using only one bit, either 0 or 1 per sample, right? I mean, here in this particular case, if I want to represent a sample, earlier we were using either 3 bits, right, or 4 bits for the representation of a sample. 3 bits were used when I was taking a 8 0 to 7 reference levels, and 4 bits were used when I was using 0 to 15, 16 reference voltage levels. Right, but here in delta modulation we are using only one bit, either 0 or 1 for one sample. Right, this is the difference. So you can see now the bit rate, required bit rate decreases rapidly, drastically. Earlier we were using 4 or 8 or 16, but now we are using only 1. Right, so we can see, so it in turn reduces the transmission channel bandwidth required for these signals. Right. So this is the working principle of delta modulation. Right. Now, how this working principle is achieved? This is achieved by making the comparison of the incoming signal with a previous signal generated from this DM modulator. Previous here means that one step previous. Then these two signals are compared, and according to that, a error signal is generated that is defined as either plus delta or a minus delta. If the error signal is plus delta, then according to that we will encode it, and if it is negative delta, then according to it we will encode it. Here it is written, and you can see if the error signal or the difference is plus delta, then it will be encoded by 1, right, bit 1, right. And if it is negative delta, then it will be encoded by 0 bit, right. So these are the 2 bits that are used for encoding these signals, right. You can see the graph here. It is the DM modulated waveform, you can see here. But before going to this waveform, I want to show you the diagram, the schematic diagram of this entire procedure. You can see here, this is DM transmitter, right. So I told you that the main components of DM transmitters are one is a 1 bit quantizer, right. I told you it is going to encode a sample by 1 bit, either by 0 or 1. So that's why it is called as a 1 bit quantizer, right. And this 1 bit quantizer's input output B and TS is sent to a summer, right, summer amplifier, and this then generate a UNTS. It is further sent to the delay circuit. Now delaying circuit is delaying it by one step. It means that if this is UNTS, then the output of this will be one step previous output, that is UN-1 TS. I mean, if we have suppose 1, 2, 3 step and I am in the third step here, right? Then the output of it will be actually this circuit will store the input of the output of the second step. So then when it comes to the third step, it will generate the output of a second step. That's why it is called UN-1 TS. Now this UN-1 TS is called as X bar NTS, and it is sent back to the summing amplifier again. So then it is mixed with the outcome, this coming output from this quantizer, and this is again mixed, and it again create a UNTS. It is done in order to make the very near approximation of the input signal, so that the input signal is properly encoded. This is the reason behind it, right? So then we will get the corresponding output, right? You can see here it consists of a 1-bit quantizer, right, and a delay circuit. I told you already, along with two summer circuits, this one and this one, right? The summers in the accumulator adds quantizer output plus minus delta with the previous sample approximation, this one, right? This gives the present sample approximation. Present sample approximation UNTS is equal to UN-1 TS plus minus delta, that is coming from here, plus minus delta, right? Or you can say UNTS is equal to UN-1 TS. You can take the common, right, and BNTS. BNTS is this signal, that is plus minus delta, right? So this is the way of working of this DM transmitter, right? In this way we will get a bit stream at the output, that is either like this 1 0 1 0. These bits are representing the samples in the incoming signal, right? Now I am going back to that graph. You can see here this graph now. Now this is what? This is the input signal, right? And this is what? This is the you can say BNTS. You recall that it was written there, BNTS, right? So this BNTS is going to be compared, not BNTS, but you can say UNTS more, correctly I can call it as UNTS. UNTS, right? So this UNTS is staircase waveform. So every time this staircase waveform that is going to the comparator, here you can see, here you can see this is going toward this side, then it is delayed by one step, and then it is compared with this. So that's what I am talking about. So it is compared with this incoming signal. So if the difference, you can see now it is higher than this one, so it means we will have output plus delta, right? You can say plus delta is added to the output, right? Then this plus delta will remain during this period, right? Then again the sample is taken at this point. Then at this point again this is higher than this. It means plus delta is again added. So in this way you can see plus delta, all these are added, and plus delta means we are getting 1 here. Now you can say it is higher than this. It means what? Now we are taking a negative delta. Step is reduced. So we have a 0, 0, 0. So you can see what I told you here, that depending upon the comparison between the UNTS and the input signal. UNTS means the staircase waveform that is delayed by one step, right? So it is compared with the input signal, and according to that the output is generated, and then after it is encoded into the bit stream. So this is the way of working of delta modulation. you can see at the mathematical part also. This is the mathematical part here. It is, you can see written here that E NTS is equal to X N Ts minus X bar N Ts. So it is obvious that this is ENTS is what? It is the error signal, that right, that is the difference of the you can see here, difference of this one and this one, right? Now here X bar NTS, I told you that it is UN minus 1 TS, the last sample approximation of the staircase waveform, right? So let's define a quantity BNTS. BNTS. This is new quantity that we defined, that is equal to delta, right, into SG N E N T S, right. This is SGN stands for signum. Signum means this function is going to be either plus delta or a minus delta, right? That's why it is, it is a sign changing function that changes the sign of this whatever difference we got. It generates a sign according to that. That's why we are calling it as a signum function, right? So B and TS is plus minus delta, right? You can see here B and TS is equal to plus minus delta. If X and TS is greater than this, you can see here. So obviously it is positive, so delta is positive. If it is less than this, then we will have a negative delta. If we have positive delta, then the code will be 1. If we have negative delta, code will be 0, right? These are transmitted, you can see here. So this is the mathematical part of this delta modulation, right? Now I am coming to the receiving part of this delta modulation. So if you look at the delta modulation receiver, you can see here, this is the input, right, that is encoded 1 0 0 1, right, 0 1 1 in this format. These are bits, binary bit stream, right, that is coming as the input. It is sent to a adder circuit, and the other input of the adder is a delay, right, delay output. Delay output means whatever output this will generate, it will send to a low pass filter. It will also send to the this circuit, and this circuit again it will produce a delayed. Delayed means one step earlier output, just like in the this case delay TS, right? So again the same thing is applied here. So then after, when the output reaches as low pass filter, it will decode that and make the approximation of that signal. You can see here the accumulator, this entire circuit is called accumulator, you can say dotted line, generate the staircase approximation of the signal output, and it is delayed by one sampling period, right? If it is then added to the this, right? If the input is binary 1, right, if input is binary 1, right, then this circuit adds a plus delta to it, right? This previous one step previous output, what was there here, so it will be added to this, right, plus delta step to the previous output. If this input is a 0, it means then step delta will be subtracted from a previous delayed signal, right, subtracted negative delta, right? So this is way how we will get the output staircase kind of a waveform. I can show you here. This is the output approximated waveform, that is staircase waveform. As I told you, it is suppose initially plus delta, then again it is plus delta, it is again a plus delta, right? Then again suppose it is a plus delta. In this way, suppose it is again plus delta, it is then plus delta again, right? So it is, you are getting a staircase waveform. Like this is now negative delta, right? In this way. So you can see this is a type of a staircase waveform. So this will be the output. You can see here, this will be the output of this, accumulator circuit. This is sent to the low pass filter. Now what low pass filter will do, right? This this is amplitude, right? This low pass filter will detect this envelope, right? You can see here. So but our signal, this is envelope is what? It was the message signal that was encoded in these waveform, these staircase, right? So then in this way we are able to recover or take out the message signal from this signal that was a DM modulator. So this is the way of working of delta modulation and demodulation. Now I am coming to the advantages and disadvantages of delta modulation. As far as advantages of the delta modulations are concerned, we know very well, I told you in the beginning that why it is used, right? It is used to reduce the bit rate and required channel bandwidth, right? These are the two main tasks. Although it is quite simple, to handle with or to deal with, circuits are easily to design, but it is suffering from a major drawback, right? I'm showing you here a pic. You look at this picture. Now you look at these pictures. The DM, as I told you, that the delta modulation is suffering from two major drawbacks. One is a slope overload distortion and other is a granular noise. Now what are these two things? You can see here, right? What is this? XT, this is the input sample. This is what? Approximated staircase waveform that I was calling UNTS there. So it is written as a UTS. Now you can see it is rising plus delta plus delta plus delta plus delta slowly. But you can see here that the slope of the input sample is high as compared to this. So this is not going to catch it. Both are running away from each other. It means we are not able to take the correct sample of the information, and it is going to create a lot of distortion in the sampled output, right? This is called slope overload distortion. It can be positive slope overload. This is the case of a positive slope overload. It can be negative. Suppose I have a this type of right, and the actual signal was like that. It initially rise it in this way and then it comes it, right? So this you can see here, this staircase is able to catch this rapidly decreasing waveform at this point, right? So this is called a negative slope overload, because here the slope of the input signal is high as compared to the slope of coming slope of the staircase waveform. It is x of t, right? So this is called negative slope overload distortion. This was called positive slope overload distortion, and this is a negative. This is called granular noise. In granular noise, you can see the step size is large, so it is not able to catch the variation in the input signal, right? So again, you can see here, it will start, I can say it will start flipping like 1 0 1 0 1 0 1 0 1, like that. So in this way, I won't be able to take the correct sample of this entire portion of the signal. This type of noise is called granular noise, right? Now these two problems are very serious problems with the DM, right? So in order to address this DM, a new type of pulse code modulation was invented, that is known as adaptive delta modulation. So in the coming lecture, we will discuss about the adaptive delta modulation, right? How we can handle this, either plus delta, plus delta, plus delta type of problem, or minus delta, minus delta, minus delta, minus delta, this one, negative slope overload. Or we will have the problem of plus delta, minus delta, plus delta, minus delta, plus delta, minus delta, right? This is the problem of a granular noise. We call it as a granular noise, or we call it as a slope overload, right? So these two problems are addressed in adaptive delta modulation, that I will discuss in the coming lecture, right? So thank you very much.